Hi, and welcome to Dr. V's AP Chemistry webcast. Today we're talking about reaction mechanisms, and this is a really big and very important topic in AP Chemistry. Here's what I'd like to accomplish in this webcast. First, we need to introduce the idea of reaction mechanisms and the idea of elementary steps, which are what we use to write reaction mechanisms, and introduce the idea of the rate-limiting step, sometimes called the rate-determining step in a mechanism. As we do this, we're going to bring in the idea of potential energy diagrams for multi-step processes and relate them to the rate-limiting step. And then we need to identify intermediates and catalysts in the mechanisms that we're talking about. And finally, we need to relate the mechanisms to the experimental rate laws. So as you can see, we have a lot to do. So let's go back a bit and talk about balanced equations a little bit. We know that balanced equations show the formulas of all the reactants and the products, and when it's correctly balanced, the coefficients show the stoichiometric ratios of all the reactants and products, which is really important. So if we look at this equation here, if this were to happen in one step, we'd have 12 particles colliding simultaneously, and that just isn't likely. That's just not very probable. And so we really want to discuss how we get from the reactants to the products, and the balanced equation simply doesn't show us that. So chemists turn to what we call reaction mechanisms, a series of steps that describe the process by which the reactants turn into the products. Even simple reactions might occur in several steps, and you can't tell by looking at the balanced equation if it's going to happen in one step or multiple steps. That's simply not what balanced equations tell us. But we do want to know, how does the process go to get from those reactants to get to the final materials? One of the big goals of chemical kinetics as a unit of study is to talk about this process and to relate it back to rate laws. Each step in the mechanism is called an elementary reaction. And what we mean by this, we might have something A plus B makes C. C plus B maybe will react to form D and E. All right. The steps that we propose in a mechanism have to add up to the overall balanced equation. So in this reaction, it would be A plus 2B makes D and E. So these elementary steps are really important. They have a single transition state. So as we go from reactants to products, notice there's only one peak in my potential energy diagram in my reaction progress, right? So I go from reactants to products, and there's one transition state. There's one activated complex to get from beginning to end. And that's what we mean by an elementary step. Now we can classify elementary steps based on the number of reactant particles that are colliding. So this is called the molecularity of the elementary step. Unimolecular, bimolecular, termolecular, how many particles are colliding, and we can actually describe that. One interesting thing about elementary steps that make them really important is that we can write a rate law based directly on the reactants of the elementary step. We can't do this for your general overall balanced equation, but we can do it for elementary steps. It's one of their really important characteristics. So let's talk about unimolecular steps. Now, a unimolecular step, right, that prefix uni means one. So a unimolecular step involves only one reactant particle. Maybe reactant A makes products. I don't even care what the products are. All that matters is that there's only one reactant particle in the elementary step. And because we can write rate laws directly from the reactants in an elementary step, it's a first order rate law. The rate is equal to the rate constant K times A raised to the first power, right? It's a first order rate law because it's a unimolecular step. Now we can also have bimolecular steps. Unimolecular steps and bimolecular steps are actually really, really common in reaction kinetics. So as you might imagine, in a bimolecular step, we have two reactant particles colliding. It could be two of the same kind, A plus A, to make products, or it could be two different materials, A plus B, colliding to make products. Either way, we're going to end up with a rate law that's second order overall. For the first reaction, where it's A plus A, my rate law would be second order in A. And in the second example, where it's A plus B reacting, it would be first order in A and first order in B, but second order overall. Now, it's also possible to have termolecular steps. We're using that prefix ter, not tri here. And this would involve three reactant particles colliding simultaneously. This is really, really unusual. I'm not saying it can happen, but it's very, very difficult to get three particles to collide in a three-dimensional space all at exactly the same time. So this is not a typical situation, but it could happen. All right, so we could have three of the same kind of thing happening. We could have one particle of one and two particles of the other colliding, or we could have three different particles colliding. We would get a third order rate law overall if the step is termolecular. So it could be third order in A, it could be first order in A and second order in B, it could be first order in A and first order in B and first order in C. They all work together, but they're all third order overall. Again, these are extremely, extremely unlikely situations. So we can have processes that occur in a single step, but many reactions occur in multiple steps, multi-step mechanisms. When we have a multi-step mechanism, one step is usually considerably slower than the other steps. One step will be slow and the other steps are really fast in comparison. As an analogy, think about making paper snowflakes. You have to take your piece of paper and fold it in half, and then fold it in half again, and you might have several series of folds in it. All right, but those are all relatively fast steps. You can fold a piece of paper in half pretty quickly. But to make the snowflake design, cutting out with your scissors, now that's a really, really slow process in comparison to folding, right? And so the cutting of all the shapes is really what determines how much time it takes to get from a flat piece of paper to hopefully a very lovely snowflake design. So we call this slow step in the process the rate determining step or the rate limiting step, because it determines or limits the overall rate of the reaction. We can't be faster than our slowest step. If cutting all the pieces out to make your snowflake takes the most time and all those other folding steps are really fast, cutting is what's going to determine how much time it takes to make your snowflake. If we want the process to go faster, we need to figure out how to cut more rapidly. So the reaction's only going to go faster if we make the slow step go faster. So let's introduce a really simple multi-step mechanism. We looked at this one before, but I hadn't said before that step one was slow. So let's assume that A plus B reacting to make C is the slow step. And then the second step, C plus B reacting to make D and E, is a fast step. So if I change the concentration of A, if I increase the concentration of A, I'm going to have more collisions between A and B, and the rate of the slow step is going to increase. The fast step will still be fast, but that means the overall reaction rate will increase because I made my slow step take less time. However, what if I were to change the concentration of C? What if I put more C into the reaction mixture? All right, so now there'll be more collisions between C and B, and the fast step would get faster, but the fast step is already fast. And the slow step is still going to be occurring at its pokey old pace. So the overall reaction rate won't really be affected because my slow step is still slow. Now I also wanted to think about the energetics of the reaction with a potential energy diagram and this multi-step mechanism, right? Where step one was slow and step two is fast. So let's say, for example, we know that it's an exothermic reaction. So we know that the reactants are higher in energy than the products. All right, but we also know there's two steps. So that means we have to have two bumps in our curve. And because step one is slow, that means it has a larger activation energy. So when we go to draw our curve, we need two peaks, and the activation energy for step one has to be larger than the activation energy of step two. And that's what I've tried to show here. So activation energy for step one, we can draw a line to indicate that magnitude. And then we can see for step two, it's a smaller step, which corresponds to step two being the faster reaction, the faster elementary step. So now I'd like to switch gears and talk about some mechanisms that have been proposed for specific reactions. We have a mechanism that's been proposed for the destruction of ozone in the atmosphere. And step one of this proposed mechanism has chlorine atoms reacting with ozone molecules to form ClO and oxygen gas. And it's been proposed that this step is the slow step of the mechanism. And in the second step, ClO reacts with oxygen atoms to make chlorine and oxygen molecules. And this has been proposed to be a fast step. So step one is our rate limiting step. I want to point out that ClO is considered a reaction intermediate. We make it and then we use it up. So you need to be able to recognize intermediates when the elementary steps of the mechanism have been written out. An intermediate is made in one step, consumed in a subsequent step. It doesn't have to be the next step, it just has to be a later step. But if we have a two-step mechanism, that is the next step. I do want to point out that in the overall balanced equation, reaction intermediates don't show up. They end up canceling out because there's one on each side. The other thing I wanted to point out about this mechanism is that Cl atoms are considered a catalyst in this mechanism. How do we recognize them as a catalyst? Well, they're consumed in the first step, and then we get it back in the second step. That's the hallmark of a catalyst when we write a mechanism. It's used in one step, you get it back in a later step. Now, I want to point out that we also don't see Cl in the overall balanced equation when we go to add these steps up. Right? So you can't say that that's a justification or a reason for identifying a catalyst, right? It's consumed in one step, we get it back in a later step. That's really the key. Now, proposing mechanisms is far beyond the scope of anything we would ask an AP chemistry student to do, but we should be able to relate it back to the rate law and determine whether or not a proposed mechanism is consistent with the rate law. And that's what we're really going to spend the rest of this webcast talking about. Proposed mechanisms have to meet two requirements. The first requirement is that the steps of the proposed mechanism have to add up to the overall balanced equation that's taking place. Otherwise, it's no good. The other requirement is that the molecularity of the slow step, the number and types of reactant particles in the slow step, must match the overall reaction order of the experimental rate law. And these are the two requirements that we need to meet. So since we've been talking about this mechanism for the destruction of ozone, let's see how it meets those two requirements. All right, we can write a rate law based on the slow step of the mechanism. The slow step is the one that determines the rate, so we can write a rate law based on the slow step. All right, so we look at the number of particles in the slow step. We have one chlorine atom and one ozone molecule. All right, so we can write that the rate equals the rate constant times Cl times ozone. All right, first order in Cl, first order in ozone, and that matches what we see in the slow step. I also want to point out that this rate law is second order overall because the slow step has two reactant particles colliding. All right, so we're trying to find that these are all consistent with each other. So in order to confirm that this proposed mechanism matches the rate law, we would need to do a series of kinetic experiments to find the experimental rate law. The mechanism has to match the rate law that we find experimentally. It doesn't go in the other order. All right, if the mechanism is going to be a valid mechanism, a reasonable proposal, it has to match what we see experimentally. So when I say the molecularity of the slow step in the proposed mechanism has to match the overall reaction order in the experimental rate law, what that means, okay, is that I need to do a series of kinetic experiments to find that experimental rate law. If my experimental rate law works out to be first order in Cl and first order in ozone and therefore second order overall, then this mechanism is consistent with that and we can say it's a valid mechanism. Proving mechanisms is not really something we can do. We can disprove them if they don't match the experimental rate law. But to prove them, that's really not something we can do. Okay, so now I'd like to go through another example of a balanced equation and the rate law and the proposed mechanism and how these pieces all fit together. So here's the reaction. NO2 reacts with carbon monoxide to make nitrogen monoxide and carbon dioxide gas. Let's look at some data. Let's work out the rate law from the data, and then we'll talk about a proposed mechanism. So if we look at trials 1 and 2, the carbon monoxide concentration is constant, but we're doubling the NO2 concentration. If we go and then look at the rate, we see that the rate has gone up by a factor of 4. Since the rate went up by a factor of 4, but the concentration of NO2 doubled when CO was held constant, that tells us that this reaction is second order with respect to NO2. So now let's look at our data and determine the reaction order with respect to CO. I just felt like changing the color of the data table. So if we look at trials 2 and 3, we see that the concentration of NO2 doubles and the concentration of carbon monoxide doubles. I don't have any trials where NO2 is constant and only CO changes, but I know that we're second order in NO2. All right, so I've got a doubling of NO2, which I know should quadruple the rate, and then I've got a doubling of CO, but if I look at the rate, it's that quadruple change, right? A fourfold change. But I can account for all of that with just the change in concentration of NO2. I know NO2 is second order from trials 1 and 2. And that means that this reaction must be zero order with respect to CO. All right, because the fourfold change in rate is solely due to the change in NO2 concentration. Changing the concentration of CO doesn't have any additional changes in the rate. So zero order with respect to CO. Oh, that's kind of important. All right, so we've got the balanced equation, and we were just looking at the initial rates data. We can write an experimental rate law from this. The rate is equal to the rate constant times NO2 squared. It's second order in NO2 and zero order in CO. CO doesn't even show up in the rate law, right? That's what it means to be zero order in CO. Carbon monoxide has to be present for this reaction to occur, But what the rate law is telling us is that the rate does not depend on the concentration of CO. As long as the CO is there, the reaction can occur, but it doesn't affect the rate. All right, but what this means is that carbon monoxide can't be part of the rate limiting step. We must need 2 steps in the mechanism. So when we go to propose that, we need to make sure that the proposed mechanism matches this. All right, so experimentally, we found the rate law to be second order in NO2. And so we have to have 2 steps in our mechanism. So let's talk about a proposed mechanism. All right, step 1 has 2 particles of NO2 colliding to make NO3 and NO. That's proposed to be the slow step. And then step 2 has NO3 colliding with carbon monoxide to make NO2 and CO2. Do the proposed steps add up to the overall balanced equation? Remember, that's one of the 2 requirements we have to meet for an overall proposed mechanism. And the answer is, well, the NO3 is on both sides, so that cancels out. And then 1 NO2 cancels out on both sides. So yeah, this does add up to the overall balanced equation. So from that requirement, we're fine. So I wanted to point out in this mechanism that NO3 would be considered an intermediate in this mechanism. You need to be able to identify intermediates from the steps, right? It's produced in step 1, it's consumed in step 2, and therefore it's considered an intermediate. Right, so it works in terms of having the steps add up to the overall balanced equation, but we have another criteria to meet. Does the molecularity of the slow step correspond to the experimental rate law? So let's look at the slow step. Step 1 has 2 particles of NO2 colliding. It's bimolecular, which means when we go to write a rate law based on just the elementary step, it should be second order in NO2. So we can go ahead and write that, and yes, it's second order in NO2, and that does match the experimental rate law, and therefore we can say that this mechanism is valid. It is consistent with the experimental evidence. Now I'd like to do one more example of a mechanism, but I'd like to do this mechanism where it involves a fast initial step, and how do we handle that situation, because it gets a little tricky. All right, so we have this equation, 2NO reacts with bromine to make 2NOBr. And kinetics experiments that we're not going to go through give the following rate law. It tells us that it's second order in NO2 and first order in bromine, right? Third order overall. Now, if this reaction were to occur in a single step, that would be telling us that, right, it's a termolecular elementary step, 3 particles colliding simultaneously. That's very, very unlikely. Anytime you have a rate law that's third order or higher overall, it's certainly going to involve more than 1 step in the mechanism. All right, and so we really do need to have more than 1 step in the proposed mechanism. So let's talk about the proposed mechanism. Step 1, NO plus Br2 undergoes a reversible equilibrium process to form NOBr2, and that's the fast step. And then step 2 involves NOBr2 reacting with another molecule of NO to make 2NOBr. Whew, okay, so I want to point out that step 1 is a reversible process. It's an equilibrium, all right? There's a forward reaction and a reverse reaction, and we need to take both of them into account when we're figuring this out. It establishes an equilibrium, and that means that the rates of the forward and reverse steps are equal. That's what it means to be at equilibrium, okay? So I do want to point out that NOBr2 is an intermediate in this mechanism. It's formed in step 1. It's consumed in step 2. So we know that the rate of the overall reaction depends on the rate of the slow step, right? And here's our slow step, and we can write a rate law based on those 2 particles. So it would be second order overall, 1 NOBr2 and 1 NO, first order in each for the rate law. And I'm calling the rate constant K2 because it's the rate constant for step 2, because I have multiple steps. Okay, but there's an issue with this. NOBr2 is an intermediate, and as a rule, we try to write rate laws that don't involve intermediates because they're not stable, they're transient, it's hard to isolate them and talk about them, so we really don't want to have rate laws with intermediates in them. So how are we going to figure out the concentration of NOBr2, right? This is really important. This is what we need to focus on right now. Well, really, it all boils down to the fact that the first step is a fast equilibrium. So we can actually use that to figure it out. So, all right, at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. That's what it means to be at equilibrium. And that's a whole unit of study all by itself. So we can write a rate law for the forward reaction of step 1. And here it is, right? NO plus Br2 to make NOBr2. So we can write a rate law for step 1. the forward reaction of step 1. I'm calling the rate constant K1 because it's the rate constant for the forward reaction of step 1. And I can also write a rate law for the reverse reaction of step 1, which is also happening. These are happening simultaneously, all right? And so the reverse reaction of step 1 has NOBr2 reacting to form NO and Br2. So I can write a rate for that step, all right? And I'm calling the rate constant K minus 1 because it's the rate constant for the reverse step of reaction 1. At equilibrium, the rates of the forward and reverse reactions are equal. That's what it means to be at equilibrium. So I'm going to set these equal to each other. But now I can take this expression and rearrange it to isolate the concentration of NOBr2, that intermediate, right? And I can solve for that. Now what we can do is, remember the rate law we wrote for step 2? We're going to substitute and put that in. So for the rate of step 2, our rate limiting step, was K2 times NOBr2 times NO. But now we can substitute the information we found from putting the rates of the forward and reverse reactions for step 1 into this expression. And I end up with the rate equals the rate constant times NO squared times Br2. Now what I did is I put all the rate constants into 1 and consolidated them as just K. Look at this. It's second order in NO, first order in Br2, and this matches the experimental rate law. So what this tells us is that this proposed mechanism is consistent with the experimental evidence, and it's a plausible, valid mechanism. And that's really what we were trying to get at. So this is actually a really important thing to remember. AP Chemistry students are expected to be able to do problems like this, okay? If the first step is a fast equilibrium, you write a rate law for the forward step, you write a rate law for the reverse step of that equilibrium step, you set those rates equal to each other and solve for the intermediate, and you're going to substitute that value into the rate law that you wrote for the slow step. You have to remember how to do this. It's not super hard. You just have to remember to do it. And these are the situations where we can end up with fractional rate reaction orders and or negative reaction orders. Sometimes fractional and negative reaction orders are situations where the first step is a fast equilibrium. It doesn't show up often on the AP exam, but it does show up there occasionally, and you need to know that it can happen and know how to deal with it. But now you do. Let's summarize everything we did in this webcast. We did a lot. All right, we talked about reaction mechanisms and how they involve a series of elementary steps. We can identify intermediates, and we can identify catalysts in mechanisms, and we can justify based on whether it's reacted and then regenerated or whether it's formed and then consumed. The slow step in the mechanism is the rate determining step. It determines the rate of the reaction, and the proposed mechanisms have to correspond to that experimental rate law. There's just so much going on. This is such an important unit, and it's really interesting. It's one of my favorite topics. Well, they're all favorite topics, but I really do love reaction kinetics. And so what I mean by the proposed mechanisms have to correspond, the number and type of colliding reactant particles in the slow step have to correspond to the reaction order in the rate law, and they have to match up. If you found this helpful, subscribe to my channel. I keep making new chemistry videos. I want you to learn as much chemistry as possible, and leave a comment if you found this to be helpful. Learn chemistry every day, study chemistry every day.